Hello again. This is Math 2232 coming to you from the College of DuPage. The title of this lecture is Parametric Equations and Curves. As always, be attentive while watching this video. By way of introduction, consider the physics experiment that many of you probably did in high school. It involved having a camera set on a long time exposure, being in a darkened room that had a strobe light flashing on and off many times during the exposure of the camera. And so you set the strobe light running. You take a picture, a long exposure picture with the camera, and while you're doing that, you release a red ball which falls freely to the ground, and simultaneously with that you kick out a yellow ball that has a horizontal trajectory, but it also starts falling to the ground. So this is the picture that you get. As seen in the strobe shot, the vertical trajectory as a function of time is independent of the horizontal trajectory. You see these given flashes, these things are at the same spot. This motivates treating x and y separately as functions of time. This is actually a common event in mathematics, science, and engineering settings, all of STEM, literally. So, either as a convenience or a necessity, we introduce a parameter t, time in this instance, to model this phenomenon. Thus, we have a coupled system of parametric or parameterized equations, x of t and y of t, which can be represented in many ways, including f of t is equal to x of t, comma, y of t. Now this is different from what we've done before. To this point in both Calc 1 and Calc 2, we've looked almost exclusively at functions of the form y equals f of x or x equals f of y, h of y rather. And almost all these formulas that we've developed require the functions to be in one of these two forms. In fact, these are functions. That means for every x there is one y, and for every y there's one x in this case. The problem is not all curves or equations that we'd like to look at fall readily or easily into this form. For example, take a circle. Now it's easy to write down the equation of a circle centered at the origin with radius r. It's x squared plus y squared equals r squared, and that's the picture that we see here. Now there's the equation and there's the circle, but note that y is not a function of x because this fails the vertical line test, and x is not a function of y because it fails the vertical line test. And that means that if we want to make them into functions, we would have to do multiple functions. Either we could say y is equal to the principal square root of r squared minus x squared, which would give the top part of the circle, or if we wanted the bottom part, we could say y is equal to minus the principal square root of r squared minus x squared, and that would give us the bottom. But we need two functions. And similarly, we could do things with x. If x is equal to the principal square root of r squared minus y squared, it would be the right side. And if we use the minus principal square root, we get the left side, but one size doesn't fit all. Unfortunately, we usually are working on the whole circle, so we can't simply say we're working on only one portion of it. Even if we narrow things down to only one of these portions, the function is still fairly unpleasant to deal with. There are also a great many curves out there that we can't even write down a single equation in terms of x and y. So to deal with these, we introduce the idea of parametric equations. That's the time that we were thinking about before. Instead of defining y in terms of x, y equal f of x, or x in terms of y, x equal h of y, we define both x of t and y of t in terms of a third variable called a parameter as follows. X is equal to f of t, y is equal to g of t. The third variable usually is denoted by t, as we did here, but doesn't have to be, of course. And sometimes we'll restrict the values of t that we'll use, and other times we won't. This will often be dependent on the problem and just what we were trying to do. Now, from your calculator standpoint, you do have this. The y equals f of x will happen when you're on this function setting in your mode, but you see PAR stands for parametric, and so you see your calculator accounts for this treatment as well. To help visualize just what a parametric curve is, here's an analogy. Pretend we have a big tank of water that is in constant motion, and we drop a ping pong ball into the tank. The point xy equals f of t, comma g of t will then represent the location of the ping pong ball in the tank at time t, and the parametric curve will be the trace of all the locations of the ping pong ball over time. Now this is not a perfect analogy, but it does give you an idea. Sketching a parametric curve is not always an easy thing to do. We're going to look at several examples, and we'll start very simply. And this first example is actually not the best way to do it, but we'll start here. So example 1, sketch the parametric curve for the following set of parametric equations. So x, in this case, you could have said x of t is equal to t squared plus t, and y, we could have said y of t is equal to 2t minus 1. You know what to do. Let's see how you did. Well, we're just going to start by picking values. So we pick values of t. So we pick t to be minus 2, minus 1, minus 1/2, 0, and 1. Don't worry about how we came up with these, but we're just picking some values. And you see we get values for x by taking t to be minus 2, substituting in there. And when we take minus 2 and substitute in here, we get y is minus 5. So we do these calculations, and now we plot the points. So you can see when t is equal to minus 2, we plot it here. When t was equal to minus 1, we're here. When t is minus 1/2, it's here. When t is 0, we were here. When t equal 1, we are up here. And so you see what we get is a curve. And moreover, and this could be a path of a particle, it's starting down here, but it's moving this way, which I would call a clockwise direction. So notice that with a parameterized curve, where we're calling this time, we do have an orientation. So that's what we get, and now we have a graph of this. And you can see this is a parabola, and we also guessed, even though we didn't plot points, we guessed that, yeah, and it starts way up down here, goes all the way, and it just keeps on going. Now, before addressing an easier way to sketch this graph, let's address the issue of limits on the parameter. You see, we went from t being minus infinity to positive infinity, so there were no limits on the parameter. But sometimes there are limits on the parameter, and this affects the sketch of the parametric equation. And let's look at that. And this is a slight variation on the previous example. Note we are having the same x of t and y of t, but now we have a limit on the parameter t. T ranges from -1 to +1. You know what to do. Let's see how you did. Okay, this is just a subset of the previous curve, so what we do is we start here and we end here. So we only get a part of the curve when we provide limits for the parameter. So the curve starts at t equal -1 and ends at t equal 1. So this was a different situation, and you want to understand this. Now we're going to, instead of just picking points, we're going to look at an easier method of sketching a parametric curve. This method uses the fact that in many, not all, but many cases, we can actually eliminate the parameter. And sometimes I say eliminate in directions to a problem, I'll say eliminate the parameter. And what we'll get is a function involving only x and y. And we call this the algebraic equation. Now there will be some issues with this, and we'll talk about that a little bit later. The two issues are knowing what part of the curve you get, and we don't have an orientation, but we'll talk more about that later. So it's important to note that we won't always be able to solve these problems, but sometimes we can. So just how do we eliminate a parameter will depend on the parametric equations that we've got. But as an example, let's talk about eliminating the parameter for this one. And here's our example. I'm asking you to eliminate the parameter from the following set of parametric equations. This is x, could have been x of t is equal to t squared plus t. And then we have y, could have been y of t is equal to 2t minus 1. You know what to do. Let's see how you did. Well, one of the easiest ways to eliminate a parameter, it's not always easy, but it's at least straightforward, is to solve this for t. Solving this for t would have been difficult, if not impossible, but solving this for t is pretty easy. So we add 1 to both sides and divide by 2, so we get that t is equal to 1/2, parentheses, the whole of y plus 1. Then we can take this for t and we can plug it into x. And so we can get the x is equal to, we're plugging this in for t, so x was t squared, so it's that business, squared, plus t, it's that business. And then we can do algebra to simplify this, and we get 1/4 y squared plus y plus 3/4. You should verify this. But note that this just gives us a set of points in the plane, and notice that the sense of orientation or direction was lost. But we can look at this equation and say, sure enough, our algebra knowledge, we can see that this is a parabola that opens to the right, and we also know the vertex is at minus 1/4, comma, minus 2. Now, to I guess I'm going to say, to recover the orientation, what you can do is you can take derivatives with respect to t from the original equations. So here we had, it was t squared plus t, so dx dt would be 2t plus 1, and dy dt is this. Now this tells us how the x's and y's changes with respect to time. So this says that this is going to be negative from t equal minus 1 to t equal minus 1/2. So it was negative. That means that the x value is decreasing. But then from there on, the x value is increasing. Now that just tells us what's happening with the x values. So you see it starts here, it decreases, then it increases. But the y tells us the up and down, and the y is constant, it's always increasing. So that tells us that we are going to get that as our orientation. So using the derivatives can be very useful in recovering the orientation. Let's do another problem. Sketch the parametric curve for the following set of parametric equations and clearly indicate the direction of motion. So we're having x, it could have been x of t, is equal to 5 cosine t. This is y, could have been y of t is equal to 2 sine t, and t ranges from 0 to 2 pi inclusive. You know what to do. Let's see how you did. All right, well, pretty much to date, we've talked about eliminating the parameter, but we've also talked about picking points. Let's just suppose we pick a whole bunch of points. So we pick, and we're looking at the fact that we're going from 0 to 2 pi, so let's just pick some values. 0, pi over 2, pi, 3 pi over 2, and 2 pi. That's in this range, and so we pick those and we plug them in and we get this. And we get these x and y coordinates. But the problem is, this doesn't really tell us what happens between. We know that these 4 points are there, but here's the same 4 points, here's the same 4 points, and here's the same 4 points. So we really don't know, based on what we've done so far, is it a curve that looks like this, a red one, a curve that looks like this, a green one, a curve that looks like this, a dark blue one, or a curve that looks like this, I'm going to call it a light blue. Now you might have intuition, but you see that really wasn't very effective just picking points. We can be fooled by just picking points. And you say, well, let's just eliminate the parameter as we did before. Let's solve for t. But then we get things that look like t equal the inverse cosine of x over 5. That means that y, for example, would be equal to the sine of the inverse cosine of x over 5. Now, this is a very awkward expression, and it really doesn't lead us where we want to go. And there's just problems with that. I'm going to just say it's awkward. So what we're going to do is we're going to eliminate the parameter in a totally different way not solving for t and substituting in. So what do? Well, here's what we're going to do. So we're going to eliminate the parameter by recalling a trig identity and the equation of ellipse. So you recall that cosine squared t plus sine squared t is equal to 1. That's a fundamental trig identity, and we've encountered that many times in our course already. So what we can do then is we can go back to the parametric equation, and we can say, well, cosine of t is x over 5, and sine of t is y over 5, or y over 2, excuse me. Now, one of your classmates asks good questions, and they will say, how did you know to do this? How did you know, how will I know to do this? And what I can bring up for them and with you is, the answer to that is pattern recognition and mathematical tradecraft. My math teachers taught me how to do it, and I remembered it. My math teacher actually who taught me this was a guy by the name of Dr. Andre de Corvin. You are being taught by me and McCabe in this case, and we're teaching you well, so you know to do this going forward. So this is what we're doing. We're solving, and we're getting cosine t is this, and sine t is this. We're going to plug it into here. So you see we're going to square both sides here, and square both sides here, and set it equal to 1. When we do that, we get x squared over 5 squared plus y squared over 2 squared, which is x squared over 25 plus y squared over 4 is equal to 1. That means that is an ellipse. From we've studied ellipses before, and we're going to study ellipses again in this course, so take this for granted if you don't remember it from your earlier studies that this is an ellipse. So we know we have an ellipse, and so we're continuing with the example, but now we know it is an ellipse by eliminating the parameter. Now we're going to have to say, well, what values does it cover on the ellipse? Because it might not be the entire ellipse. That's the second problem with eliminating the parameter. The first one was that you lose the orientation, and the second one you don't know if it's the entire curve. But by observing that cosine of t is between -1 and 1, if we multiply all the way through by 5, we know that -5 is less than or equal to 5 cosine t less than or equal to 5, and that tells us that x runs all the way from -5 to 5. Similarly, we will get that y runs from -2 to 2. And so when we build up those equations, we know that in this case, we get the full ellipse. And so it does in this case. It won't always, but we can use analysis like this to figure that out. To figure the orientation, we will use the derivatives with respect to t. And next we need to determine a direction of motion for this parametric curve. So now I will just take the derivatives like I did. So this is dx dt is -5 sine t. Now this is going to be negative from 0 to pi. That means from 0 to pi, the x value will decrease, as you can see here. And then it will start increasing down here. That came from this derivative. The y value is 2 cosine t. That means the y value is increasing from 0 to 2 pi, then it is decreasing, then it is decreasing, and then it starts increasing again. All this came from the analysis of the derivative. Make sure that you spend some time thinking about this and you understand this example. Here's yet another example. So we want to sketch the parametric curve for the following set of parametric equations and clearly indicate the direction of motion. So in this case, we're letting x equal 5 cosine of 3t, y is equal to 2 sine of 3t, as t runs from 0 to 2 pi. You know what to do. Let's see how you did. I'm going to make an observation to start with. You see the argument of this cosine and sine is 3t. So when t runs from 0 to 2 pi, we go faster around, this is going to be an ellipse, we go faster around the ellipse, and in fact 3t, I'm just multiplying all the way through by 3 on this inequality here, we get that we run from 0 to 6 pi. So you see this is going 3 times as fast. But we're going to use the same technique because we recognize the pattern. So we're going to solve for cosine 3t, getting x over 5. We're going to solve for sine of 3t, getting y over 2. And then again, we're going to use the technique. Again, this is tradecraft that now you've seen and now you know to do. Or at least you know that this is something you want to consider doing. You get cosine of 3t squared plus sine of 3t whole squared is equal to 1, but you substitute these values in, and you get that this is the ellipse that we had before. And now what we'll do is we'll check to see, well, what values do we get as we go from, as t goes from 0 to 2 pi, and we'll say, oh yes, we get the whole ellipse. So that's good, but now you start saying, well, what does it mean changing t into 3t? Well, it does change things in an important way, and I gave you indications of that up here. So you see what happens is you start here, but you go around once through 2 pi over 3. You go around twice, getting you to 4 pi over 3, and the last time you go around, we went around 3 times, gets you to t being there, but we went around 3 times. Okay, so the only differences are the values of t, and you see we did go around 3 times this circle. And by the way, if you were tracking a projectile, it could make 3 orbits like this. Now, so let's generalize that. So if we're dealing with a parametric equation that involves sines and cosines, and we're having multiples like well, the argument changes from t to nt. If n is bigger than 1, you increase the speed. It goes faster. And if n is less than 1, you decrease the speed. And here's a couple more examples. So let's look at example 6. Here we're to sketch the parametric curve for the following set of parametric equations. Clearly indicate the direction of motion. If the curve is traced more than once, give a range of the parameter for which the curve will trace out exactly once. So this has x, could have been x of t is equal to sine of t whole squared, y is equal to 2 cosine of t. You know what to do. Let's see how you did. Okay, so we're going to eliminate the parameter. However, and that means we're going to use sine squared of t plus cosine squared of t. But here we have x is sine squared of t. So here we solve for cosine t. This is y over 2. We've now done that tradecraft 3 times. So you should be getting quite comfortable with it. So we get x, because x was sine squared of t, plus, now when you square this, you're going to get y squared over 4 is equal to 1. And if we solve, we get x is equal to 1 minus, this is y squared over 4. Now this is going to be a parabola that opens to the left. And we can check the range of values, and we do that by looking at the values that happen. But you see now, even though the sign runs from -1 to 1, this ends up restricting, because the sine squared is always between 0 and 1, x will only go between 0 and 1. Now, you don't have that problem with y, but this is the range. So these are the only values we get. So it will not trace the entire parabola. So it's clear from this that we'll only get a portion of the parabola that is defined by that equation. So let's look at that part. So x runs from 0 to 1, and y goes from -2 to 2. So this is the picture that we get of that piece. So now what we have to do is we have to think about what really happens here. And in fact, we can look at some values as we go through, and we can see that when you look at some of the values for t and so on, you can see that at t equals 0, you start here. You get here at t equal pi over 2. You get down here at t equal pi. Then you start going back. You get back here at t equal 3 pi over 2, and you return to your point of origin at 2 pi. So you see this motion goes down and back up. it's a little, in fact, we talk about this being oscillatory nature of the sine and cosine. So you see we start here, go down, and then go back. So we're retracing in a backwards direction. Here is our next example. The path of a particle is given by the following set of parametric equations. X could have been x of t is equal to 3 cosine of 2t. Y is equal to 1 plus cosine squared of 2t. Completely describe the path of this particle. Do this by sketching the path, determining limits on x and y, what piece of the curves happens, and giving a range of t's for which the path will only trace out once, provided it traces out more than once, of course. You know what to do. Let's see how you did. Okay. All right. So now when you do this, you can see that the cosine of 2t is x over 3, but we have the cosine of 2t squared here. So I'm taking this x over 3, and this is going to be y is equal to 1. There's the 1 plus cosine squared of 2t, but cosine of 2t was x over 3. So this is y is equal to 1 plus x squared over 9. That's a parabola opening up. And this time we'll look at the ranges and see what happens. It certainly opens up, but now we look at this, but we see that y involves that cosine squared goes from 0 to 1. So 1 plus cosine squared goes from 1 to 2. So you see we have a restricted range again. We do not get all the x's and y's. X will run from -3 to 3, and y will run from 1 to 2. So we only get a portion of the curve, and here's a sketch of that curve. And now we wanted to talk about the orientation, so we have to think about where are we when t equals 0, and so on and so forth, and see what's going on with that. And when you do that, you see that you start here at 0. You go all the way over to here to pi over 2, but then you start coming back, and you see you start at 0. This was pi over 4. This is pi over 2. You come back at 3 pi over 4, and you get to pi. Make sure you understand what's going on here, and you see you did trace that curve going from here. So going from 0 to pi over 2, you traced it once, and when you go back, you trace it again. So you end up tracing it twice. Now, that doesn't always happen. For example, if you go back to the very first example we did in this lecture, it didn't happen there, and that parametric curve will never repeat a portion of itself. Okay, one more topic that I want to talk about in this section, and this is, we talked about eliminating a parameter. Sometimes you have to introduce a parameter, and in this case, as we say, we parameterize the curve. Now, we've seen that if we had an ellipse and also circles, if you take this x squared over a squared plus y squared over b squared equals 1, you can use a parametric substitution to parameterize that space curve as x equal a cosine t and y equal b sine t, and that will match up. This set of parametric equations will start at a0 and will trace counterclockwise, and the entire thing from 0 to 2 pi. So that's one way to do it, but you can do it a whole bunch of different ways, and these will start at different places. I am going to say in my experience, students tend to find introducing a parameter more challenging than eliminating a parameter, but there's many ways to do that. And there can be almost always many ways to do the parameterization, not only of an ellipse, but of other things, including circles. So this is something that we will be doing some in this course, a lot in Calculus 3. A couple of other very important parameters are, if you're dealing with a circle of radius r, and a circle really is a special form of ellipse, we're going to use x is equal to r cosine t and y is equal to r sine t. Now here we have a fixed circle, and we're introducing this parameterization of t. And you might say this looks a bit like polar coordinates, and we're going to talk more about those soon, but this is a fixed r. R is not a variable. And this is this is a standard parameterization for a circle. And finally, even though you might not see any reason to right now, I will tell you that it's important, and this will seem a little almost dumb, but if you have something where x is equal to f of t, or excuse me, y is equal to f of x, or x is equal to h of y, you sometimes can just say x is t, and that means that x is h of t, or you can say y is t. Actually, I was doing that backwards. If x is t, y is f of t. And then if x is h of t, y is t. Now that might seem silly, but that's actually quite useful, especially in Calculus 3. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.